Hello and welcome to all students. In this lecture we are going to study about convergence and divergence of series and the test of convergence. In the previous lecture or up to now what we have seen is geometric series, convergent and divergent series, algebra of convergent series. Now in this lecture we study the fifth point, test of convergence of a series. Then after that we will learn about alternating series, and in the next lecture we study about absolute convergence and the ratio test and the root test for the to check the convergence and divergence of the series. Okay, so in this lecture we learn about the fifth point, tests of convergence. Test of convergence. In this lecture we study some test of convergence of series. Some of the tests are mentioned here which we are going to study. So first is P series, second is comparison test for series of non-negative terms. Next is limit comparison test, that is limit form of comparison test. Next is the ratio test. Next is the root test. So all these tests we are going to study in this lecture. Okay, so let us study about the P series. So definition of P series is a P series is given by series summation 1 upon n raised to the power p. It is equal to 1 upon 1 raised to p plus 1 upon 2 raised to p plus 1 upon 3 raised to p plus dot 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 plus 1 upon n raised to p plus dot 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 where p is greater or equal 0 is a real number and this is standard well-known series. The convergence and divergence of this P series depends on the value of P. So the P series is series in the form of summation 1 upon n raised to the power p, and n runs over 1 to infinity. Okay, so this series contains infinitely many terms and the general term of this series is 1 upon n raised to the power p. First term of this series is 1 upon 1 raised to the power p, means the first term is 1. So p is, what is p here? P is any real number which is greater or equal 0. Now let us see the theorem on convergence and divergence of P series. So statement of the theorem is, if P series summation n is equal to 1 to infinity 1 upon n raised to p equal to 1 upon 1 raised to p plus 1 upon 2 raised to p plus 1 upon 3 raised to p plus dot 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 plus 1 upon n raised to p plus dot dot, where p is greater or equal 0, and this P series converges if p is strictly greater than 1, and this P series is divergent if this p is less than or equal to 1. So if p is greater than 1, then P series is convergent, and if p is equal to 1 or p is less than 1, in this case we say that the P series is divergent. Let us see some examples. Example number 1, test the convergence of series summation 1 upon n raised to 3. So we observe that example 1, the test the convergence of series summation 1 upon n cube, n is equal to 1 to infinity. Okay, so we observe that this is also a P series because this series is in the form of summation 1 upon n raised to p, and here p is 3. Okay, so this is P series. So let us write the solution. We observe that given series summation 1 upon n cube n equal to 1 to infinity is P series with p is equal to 3, and this 3 is strictly greater than 1 means p is strictly greater than 1, and by theorem of p series, when p is strictly greater than 1, in this case p series is convergent. Okay, therefore the given series is convergent. Let us take the example to test the convergence of series summation 1 upon n raised to 1 by 3, n runs from 1 to infinity. So this is also a p series because it is in the form of summation 1 upon n raised to p, n runs from 1 to infinity, and here p is equal to 1 by 3. Okay, so this is p series, and we check the convergence. We observe that given series summation n equal to 1 to infinity 1 upon n raised to 1 by 3 is a p series with p equal to 1 by 3, and this 1 by 3 is strictly less than 1, that is p is strictly less than 1, and therefore by the theorem of convergence of p series, when p is strictly less than 1, the p series is divergent. Okay, therefore the given series is divergent. So this is the simple way to identify whether the given p series is convergent or divergent. That is very simple. Now let us we study about the comparison test for series of non-negative terms. So many a time while dealing with the series, the question arises how to determine in any particular instance whether the given series is convergent or not. We try to answer the question by comparing the term of the given series with the term of the series known to converge. This idea gives us comparison test. The comparison test is applicable to only those series whose terms are non-negative. Before starting this test, let us understand the nature of the series consisting of non-negative terms and learn how they differ from any other series which have no restriction on a sign of their terms. Consider a series summation an equal to a1 plus a2 plus a3 plus dot dot dot. Since a series is constructed by adding consecutive terms of a given sequence, if any term of a sequence is negative, so called addition results into subtraction. For example, 3 plus 4 plus 9 plus 100 plus minus 70 results into subtraction of 70 from the previous sum. But if every term of a series is non-negative, non-negative means 0 or greater than 0, non-negative, then we will get something like 3 plus 4 plus 9 plus 100 plus 0 plus 0 plus 70 plus 0 plus 10 plus dot 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 dot. In this case, all terms are non-negative means either 0 or greater than 0, and there is no negative sign, which will never result into a subtraction. That is, at every stage of the partial sums, s1 is equal to a1, s1 is in the sequence of partial sum, s1 is first term, s2 is addition of first two terms, s3 is addition of first three terms, and all terms are positive. Therefore s1 is less than s2, s2 is less than or equal to s3. Okay, so okay, we are actually adding something non-negative to the partial sums of the series. Thus the partial sums of such a series satisfies this condition: s1 less equal s2, s2 less equal s3, s3 less equal s4, less equal dot dot dot, and hence these partial sums form a monotonic increasing sequence. So monotonic increasing sequence has a special characteristic. Thus the partial sums of such a series satisfies s1 less equal s2, s2 less equal s3, s3 less equal s4, s4 is less equal dot dot dot, and hence the partial sums form a monotonic increasing sequence. And we recall that a monotonic increasing sequence bounded above is convergent, and a monotonic increasing sequence, if it is not bounded above, then it is divergent. Okay, hence the partial sums related to the series summation an with each an greater or equal 0 are convergent if the sequence of partial term is bounded above, and divergent if the sequence of partial sum is not bounded above. Thus, the convergence or divergence of a series summation an with each an greater or equal 0 can be determined depending on whether Sn is bounded above or not. This principle is used in comparison test, where we compare the given series with a known series. Comparison test theorem. Let summation an be a series with non-negative terms. First statement is summation an converges if there is a convergent series of non-negative terms summation bn with an less equal bn for all n. So here comparison test. Here we are comparing two series, summation an and summation bn. So if we have a series summation bn, which is summation bn of non-negative terms and which is convergent, and we satisfy this condition, an less equal bn for all n, means a1 is less equal b1, a2 is less equal b2, a3 is less equal b3, and it is true for all n. So in this case we say that the series summation an is also convergent. And the second statement says that summation an is divergent if there is a divergent series of non-negative terms, b summation bn with an greater or equal bn for all n. Okay, so in this case, when we say this summation an is divergent, if there exists a series summation bn, we satisfy this condition, an greater or equal bn, means first term of a1 is greater or equal first term of an, or we can say that a1 is greater or equal b1, a2 is greater or equal b2, and it is true for all n's. In this case we say that the series summation an is divergent. Okay, if we have a divergent series summation bn satisfying this condition, an greater or equal bn for all n. So let us write some remarks. To apply the comparison test, we need to apply the comparison test, we need to know the series whose convergence or divergence has been established. Okay, means we must know the series whose convergence and divergence is known to us. Okay, we know the following series are convergent. First is geometric series with mod r strictly less than 1 is a divergent series, and using partial fraction for the series like summation n equal to 1 to infinity 1 upon n into bracket n plus 1 is also convergent. And next the series factorial series. Next the series summation 1 upon n factorial and runs from 1 to infinity is convergent series. It is always convergent. Okay, so we should know some convergent series. So these are the some convergent series which we are using for taking bn. Okay, the p series summation 1 upon n raised to p n equal to 1 to infinity with p greater than 1 is convergent. The p series summation 1 upon n raised to p and runs from 1 to infinity with p greater than 1 is a convergent series. P series is convergent, that we know. And also we know some divergent series also. So geometric series with mod r greater or equal 1 is divergent. The harmonic series summation 1 upon n is always divergent. The p series summation 1 upon n raised to p with p less equal 1 is also divergent. The p P series summation 1 upon n raised to p with p less equal 1 is also divergent. Now limit comparison test or limit form of a comparison test. This is a refined version of basic comparison test we discussed in the previous article. Here too we will be comparing the given series summation an with the known series summation bn. However, since this test uses an upon bn where bn's cannot be 0, therefore we must have each bn strictly greater than 0 and an's greater than or equal to 0. For symmetry, let us have an and bn both strictly greater than 0 for all n in the set of natural number. Let us write the theorem. Series summation an and series summation bn are two series with an greater than 0 and bn greater than 0 for all n belongs to n. First statement is, if limit an upon bn as n tends to infinity is equal to c and c is greater than 0, then series an and series bn behave alike. Means this limit is greater than 0, then we say that series an and series bn behaves alike. That is, series an and series bn both converges or both diverges. Second statement is, if limit an upon bn as n tends to infinity is equal to 0 and series bn converges, then series an also converges. Okay, second statement says that if the limit is equal to 0 and if series bn convergent, then series an also convergent. And third statement says that if limit an upon bn as n tends to infinity does not exist or it also tends to infinity and series bn is divergent, then series an also divergent. If limit n tends to infinity an upon bn tends to infinity and summation series bn is divergent, then series an also divergent. Okay, so this is the limit comparison test and this is the theorem on limit comparison test that is also very much useful while solving the problems. Okay, let us take one example. Determine whether the given series is convergent or divergent. Determine whether the given series is convergent or divergent. So series is given here 3 by 4 plus 5 by 9 plus 7 upon 16 plus 9 upon 25 plus dot dot dot. So this is the given series, and this series we can write the nth term of the given series can be written as. So can you guess what will be the nth term of that series? What will be the nth term of this series? So we write here nth term an is equal to 2n plus 1 divided by n plus 1 square. It is equal to, if we simplify this, then what we get is an is equal to 2n plus 1 divided by n square plus 2n plus 1. Okay, so for large value of n, what we get is, now we choose bn by using this formula. Bn is equal to 1 upon n raised to the power degree of modulus of degree of numerator minus degree of denominator of the an, and it is equal to 1 upon n raised to the power mod of 2 minus 1. So numerator, what is the degree of numerator or denominator? 2 minus 1, no problem, and it is equal to 1 upon n. 2 minus 1 is 1, mod 1 is 1, so bn is equal to 1 upon n. So we choose bn is equal to 1 upon n now. Now consider the limit of the ratio an upon bn, and it is equal to limit n tends to infinity an upon bn equal to limit n tends to infinity n into bracket 2n plus 1 divided by n square plus 2n plus 1 equal to limit n tends to infinity. And now just simplify this dividing by n square, and what we get is limit n tends to infinity, numerator is 2 plus 1 upon n square divided by 1 plus 2 upon n plus 1 upon n square. And if we simplify this, the limit value is 2 and it is not equal to 0. Therefore we apply the limit comparison test theorem. Also we know the series summation bn equal to series summation 1 upon n. This is divergent series, and therefore divergent series, and therefore series an and bn will behaves alike. Okay, therefore series an and bn behaves alike, but series bn is divergent, therefore series an diverges by the limit comparison test. Okay, and let us take next example. Example number 2, determine whether the given series is convergent or divergent. So series is not given here. Okay, so the series whose nth term is 1 upon 2 raised to n minus 1. Okay, that is the series, and for the large value of n, an will behave like 1 upon 2 raised to n. Okay, 1 upon 2 raised to n. Okay, so in this case we choose bn equal to 1 upon 2 raised to n, and let us take the limit of the ratio an upon bn. Limit n tends to infinity 2 raised to n divided by 2 raised to n minus 1, it is equal to limit n tends to infinity 1 upon 1 minus 1 upon 2 raised to n, and the limit is 1, it is not equal to 0 greater than 1. Therefore series an and bn behaves alike, but series summation bn 1 upon 2 raised to n, this series is convergent series because it is geometric series with r equal to 1/2. R means common ratio, it is equal to 1/2 and it is less than 1. Therefore series bn is convergent, and therefore series an is also convergent. Okay, whose nth term is 1 upon 2 raised to n minus 1. Now let us we study about the new series, and let us we study about the new series, alternating series. In this lecture we study what is meant by an alternating series and its convergence. An alternating series is a series whose terms are alternately positive and negative. For example, 1 minus 2 plus 3 minus 4 plus 5 minus ... This is alternating series. Second example is 1 minus 1/2 plus 1 by 3 minus 1 by 4 plus 1 by 5 minus ... This is also alternating series because the terms are alternatively positive and negative. Next example is minus 2 plus 1 minus 1/2 plus 1 by 4 minus 1 by 8 plus ... This is also alternating series. So you can construct alternating series by taking terms alternatively positive and negative. So now we understood what is meant by alternating series. Okay, the convergence and divergence of an alternating series is determined by Leibniz test. The convergence and divergence of an alternating series is determined by Leibniz test. So what is Leibniz theorem or Leibniz test, that we will see here. The series summation means alternating series. This is alternating series. The series summation n runs from 1 to infinity minus 1 raised to the power n plus 1 an, and that expansion of that series is a1 minus a2 plus a3 minus ... converges if all three of the following conditions are satisfied. Converges if all three of the following conditions are satisfied. Means this alternating series will converge if it satisfies following three conditions. So what are these three conditions? First condition is all AIs are positive. All AIs are positive. And second condition is an greater equal n plus 1, means previous term is greater equal succeeding term. Okay, for all n greater equal n for some integers, for some integer n, for some integer n. Oh yes, second condition says that nth term is always greater equal n plus 1th term, and it must be true for all n greater equal n for some integer n. And third is an converges to 0, sequence an converges to 0. Okay, let us take one example. The alternating harmonic series is given by 1 minus 1 half plus 1 by 3 minus 1 by 4 plus dot dot dot. Discuss its convergence. Now solution given that 1 minus 1 half plus 1 by 3 minus 1 by 4 plus dot dot dot, it is equal to summation minus 1 raised to the power n plus 1 as n equal to 1 to infinity 1 upon n. So given alternating series 1 minus 1 half plus 1 by 3 minus 1 by 4 plus dot dot dot, this series we can write in summation notation like this: summation n equal to 1 to infinity, summation n equal to 1 to infinity minus 1 raised to the power n plus 1 into 1 upon n. And it satisfies all these three conditions. So first condition is nth term is strictly greater than n plus 1th term, and it is true for all n in n. Also this sequence an converges to 0 and all ans are positive. Therefore by alternating series test we say that the series is convergent. And let us take some examples. Discuss the convergence of the series. So series is given here: summation n equal to 1 to infinity minus 1 raised to the power n into 4n upon 5n minus 1. Solution: here we note that the given series is alternating. Consider limit n tends to infinity, which is given by limit n tends to infinity, limit n tends to infinity 4n upon 5n minus 1, and this is 4 by 5 is not equal to 0. Therefore all these three conditions are not satisfied. One of these three conditions is fail. Therefore the series is divergent. Thus sequence an not converging to 0 as n tends to infinity, and thus the series diverges by the test of convergence. And this is the end of our lecture, and we stop here. Thank you very much.